Okay, so next talk is by Stefano Olivares from the University of Milan about quantum estimation of atomic clock transition frequency.
Thank you, Stefano. Thank you for introducing me, and thank you also to the organizer for setting up this workshop and for inviting me. And thank you all of you for being here. It's working perfect. This is the pointer. Let me spend a few words about my group in Milan. There are many activities in my pure and applied quantum mechanics group, ranging from foundational aspect of quantum mechanics, arriving to quantum information. And we have also an experimental part where in our lab, quantum optics lab, we are able to produce single photon states with different degrees of freedom, also continuous variable states. And very recently, we were able also to perform past modine detection, and not only continuous one. My interest on my side ranges from quantum information, quantum estimation, quantum optics, and quantum communication. For example, this is one of our last work in collaboration with Michele, which is here, not Nicola, where we employed weak field modine detection for optical communication. Essentially, we substitute to the piano detectors introduced by Marco Sufara this afternoon, with two PNR detectors. And so you can exploit the statistics of your detected states. And you, for example, in this paper, we show that you have some advantage in quantum communication, especially in a particular regime. This is interesting because we have a collaboration with the University of Insubria, Alessia, Levi, Mondani, Lamberti, Cassina, where we are trying to implement it experimentally. Today, I decided to show you a theoretical paper related to quantum estimation theory. The motivation is that usually we apply quantum estimation theory or quantum metrology, and then we implement an experiment. Here, we have a different approach. We know that this kind of device, named atomic clock, are the best devices which are used to measure the frequency, let's say, of time. And so we want to apply the theoretical tool to verify what happened there. It's a different kind of approach. So what we want to do is consider the bounds, the ultimate bound to precision, the statistical one, and then I will explain what I mean with statistical, to a physical system which is used to monitor the resonant frequency of atoms, which is the most precise device. So a few words about single parameter estimation here, when it wants to estimate some parameter which is not directly accessible to a measurement. We have a probe state, usually quantum probe, my topic today, which interacts with the system. Here, phi is the known parameter. Then you have your state, which depends on the parameter. You perform some measure. After that, you collect a sample of data and you choose an estimator. And the goal here is essentially to find the optimal probe to minimize the uncertainty in your estimation and find the optimal measurement to reach this kind of uncertainty. The theoretical tools here are, if you want the figure of merits, is given by the so-called Cramer-Rao theorem, which leads to this Cramer-Rao inequality, where the values of your estimator is lower bounded by this quantity here, where M is the number of outcomes here, and F is the Fisher information, where here you have the conditional probability. So you can evaluate it given the statistic of your data. From the quantum counterpart, you have the Bohr rule in order to evaluate your conditional probability. As usual, you can define this Fisher information, optimizing over all the possible measurements. This quantity here is called symmetric logarithmic derivative. And after your optimization, you finally obtain the so-called quantum Cramer-Rao bound, where you can see here the quantum Fisher information. So the best you can do according to the grid-level quantum mechanics. And if you want to be precisely complete, the eigenvalues of your LSD correspond to the optimal POVM, which is usually not clear how to implement experimentally. This is essentially a mathematical tool. Sometimes you can find a way to implement it by some tricks. Finally, to complete this brief introduction to quantum estimation, theory, single parameter at least, if you have a mixed state, then you have your statistical model, you can evaluate your quantum information this way, and also sometimes it's useful this numerical equation to obtain numerically your quantum information. This is especially useful when you have experimental data. Okay, so these are the two. I want to apply this kind of framework to two well-known system schemes in quantum optics, namely the Rabi method and the Ramsey method to estimate the frequency. This kind of method is quite simple because it involves just one single cavity. Probably most of you or all of you know that these methods correspond to send the two-level electron through a cavity. You set the interaction time to a bypass, meaning you are sending the state of the electron from ground to excited and vice versa. I introduce here the detuning between the two-level, the clock, let's say, frequency of the transition, the atomic transition, and the frequency of the cavity. After rotating, going approximation and intellectual picture, you have your Newtonian, where you can see the well-known raising and lowering operator here. This is a Siemens operator. You can evaluate the evolved state by applying simple quantum mechanics and evaluate the excited state probability. After that, you find that your excited state probability as a function of the detuning, the scale this way, depends in this way, as a maximum, of course, at resonance, where all the atoms pass from the ground state to the excited state, of course. Thanks to that, you can evaluate the Fisher information, as I told you, since you have two possible outcomes, ground state or excited state. You can evaluate it explicitly, and this is how the random information, Fisher information depends on the tuning. You can see that here there is a white dot, because in this particular point, namely at resonance, you are reaching the maximum, but here you can apply the Cramer-Rao theorem, since you have now just two outcomes, excited and ground state probabilities, but just one outcome. Because you will find always your state in the excited state. So in this case, the statistical model changes rank, and so you can apply directly your Cramer-Rao. You can evaluate also the quantum Fisher information, and so you have the first surprise here that at resonance or near resonance, you are essentially reaching the quantum Cramer-Rao boundary using the population measurement. Clocks are working at the best and the best configuration. But this is the quantum Fisher information. You see these two new peaks, which outperforms the measurement given by the population measurement, and so there is some room to improve this kind of estimation. Now, let's pass to the Ramsey method, which is the most used, essentially the one used in atomic clocks, but also in other quantum optics experiments. We see some examples during this afternoon. You have now two cavities, and in each cavity you are a pi alphas, and the free evolution time between the two cavities, in order to get the Ramsey interference there. Now, the quantum optics exercise is a little bit more complicated, since you have to apply all this stuff, but after that you can obtain an analytical result for the excited state probability after the interaction. And you can see, as expected, the interference fringes, namely the Ramsey fringes. Here, I also put in green the probability in the Rabi method, and then you can see that the peak in the activity of the Ramsey method is narrower. This is why, of course, we use the Ramsey method instead of the Rabi method in order to perform some estimation. And the number of peaks depends on essentially the free evolution time, as you probably know also in other contexts. This is, for example, one experimental result from the atomic clock in Japan, the atomic fountain frequency standard in Japan. And you can see around 100 and 110 oscillation here. And if you consider magnification near the origin, you can see that you have almost 1 oscillation per second. This is why you can estimate the frequency in such a way. You can also see this particular behavior, which is due to the coherence and the coherence state, but everything is under control. Theoretically point of view here, you cannot see this behavior because I'm considering the ultimate limits and so without any source of the coherence. This is the quantum, this is the Fisher information, starting from the probability. Again, you can see that we reach the maximum at the resonance as expected. And of course, increasing the numbers, the revolution time also increases the Fisher information. As you expect, if you have a narrower peak, you finally also increase the uncertainty, decrease if you want the uncertainty in your estimation. For example, you can expand the Fisher information around the resonance. You have this nice formula, which is useful to try to apply our theory to the actual experimental implementations. In fact, very recently we tried to apply, before our right application, let's say that we also evaluate the quantum Fisher information. And again, you can see that at the resonance, or near resonance, the population measurement, namely measuring the excited and ground state, leads you to the maximum Fisher information, but you have some room to improve further your estimation by some new measurement we have to investigate. So if you want to apply our precision to the actual atomic clocks or experiments, we apply our result to the, for example, the atomic fountain clock. This is a picture of the one at the NIST in the United States. Probably you know how an atomic fountain atomic clock works, but few words about it. Essentially, you have not an horizontal configuration with cavities, but you have just a bunch of atoms which is sent upward through one cavity, and due to the gravity, it falls down through the same cavity. And this improves reduces some uncertainty due to the difference between the cavities. And then you are proving the excited state here. So according to our theory, or the Orlando 2 Clamberell theorem, you have a lower bound for the standard deviation, say the uncertainty of the frequency estimation. And according to our calculation, you have this fractional statistical fluctuation, which depends on the Rabi frequency, the frequency of your sample, and for example, cesium atoms, and on K, which is related to the free time evolution, pre-evolution time, sorry. Now, the comparison with an experiment is not so simple, because as Alberto Porzo told today, when you want to consider the estimation of an interferometer or the stability, or rather the frequency of this kind of setup, you use the so-called Allan variance, which is an integration over time of the variances of your sample. And so in order to the comparison, you have to choose an integration time. For example, we consider here 1 second of integration time for the Allan deviation. And we consider a number of averages, namely repetition of the experiment during our setup here, in order to obtain a 10% of uncertainty, which is somehow acceptable for our investigation. So all this stuff is to understand what is the number to put here for the statistical scaling, which depends on the number of atoms. Our results are presented for a single atom, but here we have a bunch of atoms, and the number of averages corresponding to the integration time of the other deviation. So, for example, if we consider the atomic fountain clock, these are the data you can obtain from this kind of publications, and you obtain this number here. which is an order of magnitude lower with respect to the actual number. This is nice because this is essentially a lower bound. So you are expecting the experimental is upper bound, is over this kind of setup. Of course, experimentally, you have systematic errors and so on, which are not taken into account in my theory. Another kind of clock is the optical lattice clock, which is more precisely with respect to the microwave clock I presented so far. Here, your atoms are strapped into an interference pattern of lasers here, and you are probing the atoms around the scheme as usual, but now with optical frequency. Now, if you take, for example, the data from the Terbium clock, which is here in Turin, in Italy, which is a picture from here, you consider the data, you have no longer gigahertz here, but terahertz, and so you arrive to 10 to the minus 18. So this is the comparison. And you can see, of course, that the fractional statistical fluctuation in the case of the optical clock is an order of magnitude lower with respect to the fractional statistical fluctuation of the cesium clock. For example, here they use terbium. In the fluids by I use strontium, but they are essential. As I told you, in both the cases, there are almost 1 or 2 order of magnitude lower with respect to what you estimate in the actual experiments. But this is expected. This is the lower bound for these experimental devices. Now, okay. The last part of my presentation is about another configuration we can use for estimate the frequency, which is somehow used into the satellites, because it does not require to put down atoms and so on, and you can use hot vapor cells. And the idea is now to consider 3-level atoms, where the ground state usually is an upper amplifying ground state, so you have 2 levels, and this is the clock frequency you want to estimate. Usually you couple the lowest level to the 3rd level. Here you have the other laser which couple the other one. You can, it is simpler to describe this system by considering the magic representation of the Hamiltonian. Now you will see why. For the sake of simplicity, I assume that the coupling have the same strength. Here are 3 levels energy, omega 1, omega 2, omega 3. And in order to describe this system, unfortunately, we have to consider, or fortunately, we have to consider the relaxation rate of the ground state coherences affecting the level 1, 2. We have also to consider the relaxation rate of the side state, because now we have an vapor cell, and so they are colliding each other, and all this stuff leads to some losses of energy here. And so after that, you can write down a master equation approach, going to retorting wave approximation, perform adiabatic approximation. And if you assume absence of saturation and introduce this laser pumping rate, you can find the steady state of your system. And in particular, I use the density operator analysis, and we can focus on the population of the 3rd level, which has this behavior here, which goes down to 0, almost to 0, when you are at resonance. So when you are at resonance, essentially, you have that the fluorescence signal, namely the transition from the 3rd level to the ground state, disappear. And this is known as dark line, because when the first time they show it, there was a cell lighted with a laser, there was some fluorescence. This here you have a gradient of the magnetic field along this z axis, and of course, due to the gradients, the splitting of the 2 Zeeman level changes. And essentially here, when the fluorescence disappear, you are coupling exactly to the 3rd state. Generally, there is also the tuning, but it's not so important. And so you can see this appearance of dark light. Now, this can be better understand if you consider not the actual level 1, 2, 3 of your atom, but this coupled and uncoupled level, namely the symmetric and asymmetric superposition of two states here. Because in this case, you can see that the coupled level is coupled to the third level, of course, and the uncoupled level is uncoupled to the third level. You see that the transition, that the whole element goes to 0 here. So what happens is that essentially you are pumping the level to the third state, but due to the spontaneous emission, they go down with equal probability in our setup to the lower level. But once they arrive here, they are trapped. So you have the coherent population trap. Now, you can see also the behavior here, where the population, as the third level is going to 0, the population of the third level, you are populating the uncoupled level, and you are populating the coupled level. So we can apply now our estimation theory, measuring this disappearance of the signal, and this is the Fisher information corresponding. As you can see, you have no longer a maximum here 0, essentially because now you have the presence of the coherence, namely due to the coherence between these two levels, and essentially because in this point you are not going to 0. So if you perform all the calculation, you see that this is essentially 0, but it is quite clear. Also, if you consider a classical optical interferometer, if you want to estimate the phase shift, you don't go into the maximum of the fringes, but it's better to stay where the derivative is larger. Here you have the Fisher information, and you can see that if you measure the coherences, namely the red lines, you can reach almost the best you can do, namely the quantum Fisher information. Whereas if you measure the population level, you have a worse result. The quantum information can be defined this way because now you are no longer a pure state, but you have a statistical model. As I told you, if you set to 0 the coherence, namely the relaxation rate of the ground state coherence, you can see that you are going to the maximum, as you expected. For completeness, I show you what happens if you consider the measurement not of all the states, but if you just measure the coherence. Here, what happening if you're measuring the superposition of two states, if were able to measure them, because it's not so simple. There are some experiments going in that direction, but it's not so simple to implement this measurement of coherences. That's not impossible. And if you measure the coupled and uncoupled state, you can see that you are almost reaching the best you can do about quantum mechanics, also in the presence of some noise. Okay, I think I'm done. So I can tell some joke also. No, it's not the case, I think. So just to summarize, I show you quantum estimation theory applied to the most accurate device. I try also to apply our theory to the experimental number you can find into the papers. We, of course, found some known results, meaning Ramsey interferometry is better with respect to gravity 1. But we have shown that there is room to improve this kind of setups. Of course, understanding which is the actual measurement we have to perform is not so simple. We are working in that direction. We are also applying some, you can find some details in this paper. We are applying also some decoherence into our analysis. For example, we are applying the quantum decoherence there into the cavities, but similar result can be obtained if you have some problem in the exciting states. And I will finish saying that we are still working on the optimal measurement, especially its experimental feasibility, in order to improve this kind of estimation. So thank you for your attention, and thank you for who founded this kind of research.